Hello dear viewers, I welcome all my friends for this tutorial 2 on network theorems. I hope that all of you have seen the first tutorial, that is tutorial 1 on this network theorems. This is one more problem. Now see, this is our second problem in our tutorials, and this problem is like this. The problem statement is find current in 12 ohm resistor. I hope that you have seen the first tutorial, because in that tutorial 1 I have given you one idea of replacing the branches or representing the branches containing the current sources in a typical manner. Okay, so I hope that everybody knows that idea now. So let us first solve this problem with Kirchhoff's laws. Okay, so we first find the solution of this particular problem with the help of Kirchhoff's laws. Remember, our problem is to find the current in 12 ohm resistor. Our 12 ohm resistor is located here. Now look at the circuit. In this circuit there are two current sources. One is here, that is 15 ampere current source, and the another one is here, that is 10 ampere current source. So we have done the same thing for both the sources. Now our circuit will be ready to be operated with the help of Kirchhoff's laws. Now see, what is our problem? Our problem is to find the current in the 12 ohm resistor. Now see, how many loops are there? Closed loops or meshes are there? See here, this can be one of the meshes or closed loops, one. This can be second, from this point here down, left and again to the top. This will be one more loop, second loop. But there can be one more loop also, third loop, this entire one. From this point here, then down towards the left up to this point and here. So we can have three loops or closed paths. Now let us have a current distribution. You will find that the basic meshes in the circuit are only two. This is 1 and this is 2. Why we are doing that? Why we are finding out the smallest loops or meshes? Because that gives us idea how many current variables will be required. So we will find that this is the smallest loop here, and this is one more smallest loop here. Whereas this third loop was not the smallest one. So these two are the basic meshes. So that means we will need two current variables. So let us start the current distribution now. Start from this corner. So 15 ampere current is supplied at this node. Now there is a bifurcation. So we have to assume first variable at this particular point. Suppose we assume that a current I1 flows. Now why I am saying I1? Because I have taken a judgment from the number of meshes that how many current variables will be needed. And we know that we will need two current variables for the current distribution. That means we can say I1 and I2 will be our current variables. So I assume that I1 is coming down. So what will be the current going ahead in this direction? It will be 15 minus I1. Okay. So 15 ampere is coming or supplied at this node. Out of that, I1 is going away from this node. That means in this particular branch, the current which is moving away from this node will be 15 minus I1. Now that current reaches here, 15 minus I1 reaches here. Again there is a bifurcation, because some current will flow through this branch and some current will flow through this branch. Here also we need to take one more variable. Suppose we take I2 here, like this. Now what will happen? Out of 15 minus I1, I2 is also going out, or I2 is also subtracted. So what will be the current moving ahead? The current moving ahead here will be 15 minus I1 minus I2. And see here, when this current is 15 minus I1 minus I2, and when it reaches to this node, 10 ampere current is going away from the node. So this 10 ampere will be subtracted. So out of 15 minus I1 minus I2, which comes here, 10 is going out. That means what will be the current moving ahead? I will show it here. 15 minus I1 minus I2 minus 10. That means 5 minus I1 minus I2. That will be the current. And it will flow through this 9 ohm resistor. It will come to this node. Okay. Now see what happens at this node. At this node, from this branch, current of 5 minus I1 minus I2 is coming. And this 10 ampere will be added. So what will be current moving ahead here? It will be again 10 plus 5, 15. So 15 minus I1 minus I2. Now this current reaches here at this node. 15 minus I1 minus I2 reaches here. and this I2 is further added into that. So what will be the current moving away from this node? So it will be 50 minus I1. And now at this node, this 15 minus I1 will be coming, and this I1 is added. So what will be current moving away? That is 15 ampere. And see, it exactly matches here. So this will be the current distribution. And now first law, Kirchhoff's first law we have applied. Now just to apply the Kirchhoff's second law. In second law, we identify the loops and write the loop equations. We have two variables, so we need only two equations. So let us take this first small mesh as the loop 1. See here, loop 1 will be like this. From this point, here, down, left and top to the original point. That will be loop 1. And loop 2, we will select like this. Okay, from this point, here, then here, down, left, further left, and again top to the original point. Here, this will be loop 2. And just very fast, let us write down the loop equations. So for loop 1, what will be the equation? The equation will be, let us start from this corner, from this node, no component in this travel, so no voltage rise or drop. Then coming down, there is a resistance. Resistance is 12 ohm, current is I2, but we are moving in the same direction of current, so minus 12 I2 here. So minus 12 I2. Now further, we have reached here. We come to left. Again, no component in this path, so no voltage rise or drop. And then we will go back to the original point. Now in this travel, there is a resistor, 18 ohm, and the current is I1. But now see, when we are traveling from bottom to top, current is opposite. That means we have to take this as voltage rise. So plus 18 I1. So plus 18 I1. And now we have reached the original point, and so it will be equal to 0. Let us simplify it. It will be 12 I2 equal to 18 I1. That means I2 equal to 18 by 12 I1. That means it is equal to 3 by 2 I1. And we call this as equation 1. Now for loop 2. What will be the equation for loop 2 now? Our loop 2 is this. From this point, then this will be the travel. Okay. Now let us start from this point. This to this, entire up to this, no component, so no voltage rise or drop. This to this, nothing. And now this to this. It will be 9 ohm resistor and current is 5 minus I1 minus I2. But it will be a voltage drop. So minus 9 into 5 minus I1 minus I2. Now after this, from this point again, no component. Here also no component. And from this point to original point or starting point, it will be 12 ohm resistor and current is I2. But current is coming opposite, so it will be plus 12 I2. So plus 12 I2. And all this will be equal to 0. Let us simplify it. This will be minus 45. Then plus 9 I1 plus 9 I2 plus 12 I2. This will be all equal to 0. Let us simplify it further. I1 terms 9 I1. I2 terms 9 plus 12, 21 I2. And this 45, let us take to other side, that will be plus 45. Let us see whether we can further simplify. Yes, we can say divide further by 3. So 3 I1 plus 7 I2 equal to 15. So this will be our equation 2. Okay. So rest job, you know what job is remaining? Just to solve these two equations simultaneously and find out the answers I1 and I2. However, as per our problem statement, we are only interested in finding out the current in 12 ohm resistor. As per our current distribution, the current of I2 is flowing through this 12 ohm resistor. That means we are interested in finding out the value of I2. Okay, so solve the equations and find out the value of I2. Let the value be plus or minus. We will see the significance later on. But our first job is to solve these equations. You can pause your video and you can solve the equations on the paper and then resume the video. So solve the equations. I hope you have solved the equations correctly. and see the answer I have written here. The I2 current as per the current distribution is 5 by 3 ampere. Now see, you are getting a plus value there. What does it mean? It means that whatever direction we had shown earlier, because earlier we just do the current distribution blindly. We don't know initially what would be the final direction of the current. But as we had taken this direction from top to bottom, and as the answer is coming out to be positive, that means this direction is true. So as usual, let us just mark these terminals as A, this point, and this point as B, so that we have to write the direction also. So we can say that the current flowing in 12 ohm resistor will be 5 upon 3 ampere, and its direction will be from point A to point B, or from node A to node B. So here at the end you will just write a statement that current in 12 ohm resistor is equal to 5 by 3 ampere, and in bracket you will write from A to B. Okay, so this will be the answer with the help of Kirchhoff's laws. Now let us move to the solution with, say, Thevenin's theorem. Okay, so the same problem we will consider, and we will apply Thevenin's theorem, and let us find whether we are getting the correct answer or not. Now for Thevenin's theorem also, we can use our same idea of replacing the branches which we are having or which are having the current sources. So let us do it very fast. For this current source 15 ampere, as usual, we will just replace it like this. This is sending the current from this. So 15 ampere I will write here, going to this node, and 15 ampere coming from this node like this, and then just scratching this from the diagram like this. Okay, so first branch or first current source we have removed. Also here same idea we can use. From here the current coming down will be 10 ampere, because see the direction is downwards, and here at this node the current supplied will be 10 ampere, and after that we will just remove this source from the diagram and keep the terminals hanging or floating. Now this will be the circuit which we will use for applying the Thevenin's theorem. See, this is our resistance in which we want to find out the current. Now see, let us start with the procedure of Thevenin's theorem. What is the first step in Thevenin's theorem? The first step is that we have to remove the resistance in which we want to calculate the current from the circuit. Okay, so 12 ohm is our load resistor. And what is first step? The first step is that the load resistor is to be removed from the circuit. So that we will do. So I will just remove it from the circuit. Okay, so this we have removed. And further, whatever open terminals we get or open ports we get, we have to conveniently mark them with some letters. So suppose A and B like this. Okay, so first step we have done. Here somewhere we will write RL, load resistance, is nothing but 12 ohms. So first step is over now. What is the second step now in Thevenin's theorem? The second step in Thevenin's theorem is we have to distribute the current in the circuit so obtained, and then find out the various branch currents. So let us distribute the current. You will find now in this circuit how many loops we are getting. We are getting just one single loop like this, because see, it is open here, it is open here. So one single loop we get. So for finding out the current, we need to take only one variable. Let us start from this corner. Now see, 15 ampere is supplied at this particular node. Okay, let us assume that some current I flows here. So 15 ampere is supplied here. Out of that I ampere goes down. What will be the current moving ahead? Here it will be 15 minus I. Now see here, this current will reach here. Will it move through or flow through this branch? No, because it is open here. So the same current 15 minus I will move ahead. Now it will reach to this particular node. So out of 15 minus I, which is reaching here, 10 ampere is gone. It is going out of the circuit. So what current will remain here? Going ahead, I will show it here. 15 minus I minus 10. So 5 minus I. Now see, this 5 minus I will flow through this 9 ohm. and it will reach up to this particular point. What happens at this node now? 5 minus I is coming like this, and 10 ampere is added into that. So current moving in this direction will be 15 minus I. Now this 15 minus I will reach here. See, this is open, so no current is coming or going in this particular branch. So this entire 15 minus I will be moving ahead like this. And now see what happens at this particular node here. This 15 minus I is coming like this, and this I is adding. I is adding into that. So 15 minus I plus I will be 15 ampere. And see again, 15 ampere is going out. So our current distribution is proper. Now since we are getting only one current loop, we will just mark it like this. So here I will write now loop equation, because our job is to write the loop equation now and to find various branch currents. What will be the loop equation? See, we traverse the loop now. This, remember, the loop will be entire loop like this, that we have to traverse. So starting from this end, now this point to this point, no component, so no rise or drop. Here to here, again no component. Here to here, no component. From here to here, there is 9 ohm resistor, and current is 5 minus I. But it will be negative. So minus 9 into 5 minus I. Now we have reached here. Now this to this, again no component. Now see here, this to this, again no component. This to this, no component. And now this point to the initial point, there is one resistor, 18 ohm. Now see, we are traveling from bottom to top, but the current is from top to bottom. So it will be a voltage rise. So voltage rise will be 18 into I. So plus 18I. So this will be the term. And now we have traversed the entire loop. So this all will be equal to 0. Let us simplify it. This will be minus 45 plus 9I plus 18I must be equal to 0. So further, 18 plus 9 is 27. So 27I must be equal to 45. And so I will be equal to 45 upon 27. We can divide numerator as well as denominator by common factor, say 9. So it will be 5 by 3 ampere. Okay. So second step is over. Now third step in Thevenin's theorem is to find VTH. So I will write here the next step as to find VTH. So we will go as per this step now. We will connect an imaginary voltage source across these 2 points. Suppose I show it like this. Now you may show in the reverse way also, that is your choice. Okay, so we can show like this, means positive to A, negative to B, or in a reverse way, positive to B and negative to A. That is our choice. But here this value will be VTH. Now what is the next procedure in this step? We have to select such a loop, closed loop or closed path, but that must contain the VTH. So this is one. So here, then through VTH, left and to the top. Or otherwise, there is one more path available now, which contains VTH. We start from this, come here, then down, then to the left, and then through VTH to the original point. So either we can take this first closed path, or we can take this second closed path. Remember, whichever closed path you take and write down the loop equation, finally you will get the same answer. You calculate it with first loop or calculate it with the second loop. You will get the same answer. Let us take this smaller one, first one. Okay. So we will select this closed path. And now let us write the loop equation for this particular path. Start from this point. This to this point, no component. From this to this, see, we are moving down, but battery is opposite. That means we are jumping from positive to negative. So it will be a voltage drop. So it will be taken as minus VTH. So we reach here. Now to the left, again there is no component. And from this point to the top, we are moving like this. Current is opposite. So it will be plus, means a voltage rise. So plus 18I. So plus 18 into I must be equal to 0. That means VTH must be equal to 18I. And see, we have calculated earlier value of I, that was 5 by 3. So 18 into 5 upon 3. So this will be 30 volt. Okay, so VTH value comes out to be 30 volt. Okay, so VTH we have calculated. Now the step 4. Step 4 will be to find the value of RTH. So next step is to find RTH. Now here the previous say finding of VTH, I will write it here because we have to compile the results after every steps. So VTH was coming as 30 volt. Okay, and now to find RTH. So here A and B points. Okay, so this branch will be just 18 ohm. So our circuit will be like this now. This is 18 ohm to be shown here. Then here like this. This was point A. To the other side here, only this resistance of 9 ohm. Remember, this is open here everywhere. We just want a passive circuit. So you will find towards the left of these points AB, this 18 ohm is there, and towards the right, it will be this 9 ohm. So it will be 9 ohm here. Okay. Now remember, there was no voltage source in this. Otherwise, if there would have been a voltage source, we would have shorted it. The diagram clearly shows that this 18 ohm and 9 ohm are in parallel across points A and B. So what will be the net resistance of parallel combination? Product divided by sum. So 18 multiplied by 9 divided by 18 plus 9. So it will be equal to 18 multiplied by 9, and in the denominator it will be 27. So 9 3s are 27 and 3 6s are 8. So what value we get for equivalent resistance? We get it as 6 ohm. Just record that value of 6 ohm as RTH like this. Okay. So we have now calculated both VTH and RTH for the given circuit. And so what is the next job now? Next job is to draw the Thevenin's equivalent circuit. So that we will do. VTH was 30 volt, RTH was 6 ohm, and the load resistance RL was 12 ohm. And what is the formula to calculate the current? See, suppose current is now like this. Suppose we say that this is the current I. Then what is the formula to calculate I? I must be equal to VTH divided by RTH plus RL. So put the values. So VTH is 30, RTH was 6, and RL is 12. So it will be 30 by 18. So it will be 5 by 3 ampere. See, now we are getting the same answer for the current flowing through the load resistor. What about the direction of current flowing? See here, VTH we had assumed like this, positive to A and negative to B, and then we had got plus answer for VTH. That means the directions of VTH assumed in the circuit were correct, and since positive plate was connected to A and negative to B, it means that point A was at a higher potential and point B is at a lower potential. That means if really load resistance is reconnected here, the current would flow from A to B. So here we will write in bracket that current is from A to B. Okay. So this will be the answer with Thevenin's theorem. We are getting the same answer as we have obtained from the application of Kirchhoff's law. And now let us move towards the Norton's theorem. Same problem we will solve with Norton's method. Now let us apply the steps of Norton's theorem. Again, we have drawn the same given circuit, and our job is to find out current in this 12 ohm resistor. So first step is same in the Norton's theorem, just like the Thevenin's theorem, that to remove the load resistance from the circuit and mark the open terminals as A and B. But before doing that, again we can take benefit of our idea of replacing the branches of currents. This we had shown 15 ampere like this. So here 15 ampere, then 15 ampere coming out from this, and then we just scratch this from the circuit. So it will be this thing for first source. For second source also we can repeat it. 10 ampere is coming down here, and 10 ampere is further supplied to this node, 10 ampere, and so here we can remove it. Okay, so we can use the same idea of replacing the branches which were having the current sources. So this also we will keep as floating. So we can start even for Norton's theorem with this particular circuit. Okay, now the first step. First step is to remove the load resistor and mark the open terminals with suitable letters. So we will do that. So first step is this. Load resistor removed and the terminals marked as A and B. And here we will write the load resistor as the 12 ohm resistor. So first step is over in Norton's theorem. Now what is the second step in Norton theorem? Second step in Norton theorem is that we have to temporarily short circuit these 2 points A and B, and we have to find out what current would be flowing through this shorted link. So here we will adopt the second step now, that we will short circuit the 2 points A and B. In this step, we should calculate the current flowing through this shorted link. Once we find out that value is nothing but the value of IN in the Norton's theorem. But let us find out this value. So we have to do some current distribution. That means we have to take help of our Kirchhoff's laws. So we start from this end. 15 ampere is the current flowing here. So here suppose I say current is I1. So 15 ampere is coming here. I1 is moving down. So what current will move ahead? Here it will be 15 minus I1. Now this 15 minus I1 will reach here. Again through this shorted link some current will flow. So I will say that it is I2. So what current will move ahead? Current here will be 15 minus I1 minus I2. Will be this current. Now say out of this current 15 minus I1 minus I2, 10 ampere is taken out, or it is moving out of the circuit. So what current will flow in this branch? This minus 10. So 15 minus 10 is 5. So it will be 5 minus I1 minus I2. Now this entire current will move up to this point and it will reach here. Now this current is reaching here. 10 ampere is added into that. So current here will be 15 minus I1 minus I2. Now add this node. This is 15 minus I1 minus I2. This I2 is added. So current here will be 15 minus I1. And now at this node, 15 minus I1 is coming like this. I1 is coming from top. They will add. So current going out of the circuit will be 15 ampere. So again our current distribution is proper. Now just to calculate the value of current in the shorted link. Now look at our figure. In our current distribution, we have shown this I2 as the current flowing through this shorted link. Okay, so we are interested only in value of this I2. But we have to solve the equations for that. Before that, we have to write the equations. So let us take this first mesh like this. We will call it as 1. And let us take this one as the second mesh. We will call it as 2. So write the equations. So for loop 1, what will be the equation for loop 1 now? Let us start from this point. Here to here, no component. Again, here to here, again no component. Then from here to here, again no component. And from this point to the original point, it is 18 ohm resistor and current is I1. But it will be plus 18 I1. So plus 18 I1, but it all must be equal to 0. That is what we can say I1 is equal to 0. Is the first equation. And now for loop 2. So let us write very fast what is the equation for loop 2. Our loop 2 is like this. So let us start from this point. No component here. Here it is 9 ohm resistor and current is 5 minus I1 minus I2. So minus 9 into 5 minus I1 minus I2. Now we reach here. Again this to this no component, this to this no component, and from this point to this point again no component. This all must be equal to 0. Okay. So let us simplify it. Minus 45 plus 9 I1 plus 9 I2 must be equal to 0. Okay. That means in short it will be I1 plus I2 equal to 5. That is our equation 2. And now our job is to solve these two equations, but we are interested only in the value of current flowing through the shorted link, means we are interested only in the value of I2. Remember, you can even substitute this I1 is equal to 0 here. So if we substitute I1 equal to 0, the simple answer I2 is equal to 5. So here we can write hence I2 equal to 5 ampere. And now see what is I2. In fact, I2 is nothing but the current flowing into the shorted link. But according to Norton's theorem, this is the value of IN, that equivalent current source. So here I will write this must be also equal to the Norton's equivalent current IN. So that value we have calculated, we will just write it here. So IN equal to 5 ampere. And now third job was to calculate value of Rn, Norton's equivalent resistance. Rn is nothing but, its meaning is same as RTH in the Thevenin's theorem. We already know what was that value. That value we had got for RTH as 6 ohm. So directly I will write here the value of Rn will be equal to 6 ohm. Now the final step, we have calculated all the required values RL, IN and Rn. So just to draw the Norton's equivalent circuit. Norton's equivalent circuit is like this: a current source IN, then a parallel resistance, that is Rn, and then this will be the two ports A and B, like this, and then we replace our load resistance across A and B. So this will be the Norton's equivalent circuit. Now here IN we had got 5 ampere, Rn we had got 6 ohm, and RL was 12 ohm. And what was the formula? Suppose we say that the current flowing through the load resistor, if it is I, then as per the Norton's theorem, this value of I means the current flowing through the load resistance must be equal to the Norton's current IN in bracket Rn divided by Rn plus RL. Just introduce the values or substitute the values here. The values will be like this. This IN is 5 in bracket. In the numerator Rn was 6. In the denominator Rn plus RL. So 6 plus 12. And let us calculate it. It will be equal to 5 into in bracket 6 by 18. So it will be 5 by 3 ampere. So again we are getting the same answer with the help of Norton's theorem. So current in the load resistor must be equal to 5 by 3 ampere in magnitude. Let us talk about the direction. See here, as per our current distribution, this I2 was flowing from A to B. This is our IN. That means the direction is clear here at this particular step itself. So the current was flowing from A to B because we have got a plus value for this I2. Okay, so here we can write in bracket from A to B. So in general, this is the procedure of solving any given problem with the help of any given methods. Okay, so this is one more problem which we will solve again by Kirchhoff's laws, Thevenin's theorem and Norton's theorem. But here now we will go very fast because we know all the procedures, we know all the rules. So every time I will not explain the things now. So very fast we will try to solve it. Okay. There are three sources, power sources. One battery means voltage source, and the other two sources are the current sources. So as per our usual procedure of replacing the current sources in a typical manner, I will just do that. So 5 ampere current here. So this 5 ampere input, 5 ampere coming out from here. So this will go. And for this 2 ampere, I will just mark 2 ampere current like this and 2 ampere here. And then again we remove it as usual, keeping the points hanging, wires hanging like this. And see, this will be our circuit. We have written here, we will first find out the solution with the help of Kirchhoff's laws. Now the clear observation of the circuit will show that there is only one loop. So one variable will be needed. Let us start the current distribution from this point. I will say that this current is I, one current variable, so that current flowing down will be 5 minus I. And now this I will flow through this battery. Then this I current will be coming over here. What happens at this node? This 2 ampere added. So I plus 2 current will move ahead like this. So current here also will be I plus 2. This I plus 2 will come over here. Out of that 2 ampere goes like this. It is going out of the circuit. So current flowing here will be I. And this I current will reach here. And 5 minus I is added. So current will be 5 ampere leaving this node. So our current distribution is proper. Now only one loop is there. So just this will be our loop. See, the loop will be like this. This point here, down, left, and back to the original point. So I will write here the loop equation would be. So very fast we write the loop equation now. Starting from this point. The battery is here. We are jumping from, our travel is clockwise. So we are jumping from positive to negative, so voltage drop. So minus 6. Next, we reach here. Then no component. Here component is 4 ohm resistor. Current is I plus 2. So minus 4 times I plus 2. Next, we come down. Here no component. And here there is a component, 2 ohm resistor. Current is 5 minus I, but this will be voltage rise. So plus 2 times 5 minus I. Plus 2 times 5 minus I. And this will be equal to 0. Let us simplify. Minus 6 minus 4I minus 8 plus 10 minus 2I must be equal to 0. So here minus 4I and minus 2I is minus 6I. And all constants minus 6 and minus 8. Minus 14 plus 10 is minus 4. So minus 4 equal to 0. That gives us minus 6I equal to 4. Is I equal to minus 4 by 6. That means I is equal to minus 2 by 3 ampere. Now see, we are getting a negative answer. But let us now see what was our problem. Our problem was what would be the current flowing through this 4 ohm resistor. As per our current distribution, current flowing through this 4 ohm resistor is I plus 2. So here we can write, hence current in 4 ohm resistor will be equal to, what is the current as per distribution? I plus 2. So I plus 2. Let us substitute the value of I. Remember, whatever value you get, plus or minus, you have not to alter it. So minus 2 by 3 plus 2. So what will be this answer? 4 by 3. So 4 by 3 ampere. And the answer is coming plus. The answer is coming plus. Means whatever direction of current we had assumed in this way, that direction is correct. So with Kirchhoff's laws, we have calculated the answer as the current is 4 by 3 ampere. And what would be its direction? Suppose now we mark these terminals as A and B. Then current must be flowing from A to B. So here I will write from A to B. Okay. So this will be the answer. Current is 4 by 3 ampere and direction is A to B. Now the solution with Thevenin's theorem. Again, as a starting point, we can replace the branches containing current sources with our regular procedure. So for Thevenin's theorem also, we can do that. Okay, so very fast I will do that. So 5 ampere here, 5 ampere. Then remove this. Here also 2 ampere supplied here. 2 ampere taken from this node. And also here we will remove this. So this will be the starting point to implement the procedure of Thevenin's theorem. First step in Thevenin's theorem is to remove the load resistor. Our load resistance is 4 ohm. So just let us remove it. Okay. So we remove it and then we mark the open terminals as A and B. So that we have done here, and here we will write RL equal to 4 ohm. So step 1 is over. Now what is step 2? In step 2, we have to distribute the currents in the circuit so obtained and then find out the values of various branch currents. Now if you look at the figure, you will find that as such there is no closed path. But a current of 2 ampere is supplied at this node or it is taken from this node. That means in certain part of the circuit, certain currents would be flowing. Let us just see what happens. Now see, suppose this 2 ampere is supplied here. Can any current move through this particular branch? No, because there is an open circuit. So this entire 2 ampere will come towards left like this. Okay. Now this 2 ampere will flow through this battery and reach up to this node. What happens at this node? 2 ampere coming like this, and then 5 ampere is also supplied. So what will be the total current coming down? It will be 7 ampere. Now this 7 ampere current will reach here at this node. Out of that, 5 ampere is going out of the circuit. So what will be the current moving in this direction? It will be 2 ampere. And now see, this 2 ampere will come over here. Will any current move here? No, because there is open circuit ahead. That means all this 2 ampere current will leave the circuit, and see, our current distribution is exactly matching. Okay, so step 2 is over and we have found out various branch currents. And now let us move to the third step. The third step is to calculate VTH. Now what we do in this particular step? In this particular step, we assume some imaginary voltage source across the open terminals A and B. Let us do it this way. So I just show a voltage source in this fashion connected across the open terminal. You can connect this voltage source in opposite manner also, in a reverse manner also, and its value is VTH. Okay. Now what is the next step? Means what is the next procedure? That we have to consider such a closed loop in which VTH will be included. Now let us see, after connecting VTH, we get certain closed loop. So this entire thing only will be a closed loop in the given circuit. So our closed loop will be from this point here, then down to left up to this point and to the top to meet at the original point. So our loop will be this entire loop. Let us write down the loop equation. Starting from this point, this to this point, it will be -6. Then next we reach here. No component here. Here it will be minus VTH. Then we reach here. Again no component up to this point, and from this point to this point it is 2 ohm resistor and 7 ampere current. And it will be a voltage rise because current is coming opposite. So plus 2 into 7, and this all will be equal to 0. That means VTH is equal to, this VTH we take to other side, so 14 minus 6, that means it will be 8 volt. So we have calculated the value of open circuit voltage across points A and B, and that comes out to be 8 volt. Now see the meaning. If as we are getting a positive or plus answer here, that means the polarities of VTH are correct. That means point A is at higher potential and point B is at lower potential. Means when actually the load resistance is reconnected here, the current would be flowing from A to B. Okay. Now this step is over. What is next step? Next step is to calculate the equivalent value of resistance for this given circuit. Now here, next step would be to calculate RTH. Now see, for calculation of RTH, we need only the passive circuit across points A and B. Okay, so let us do that. Now see, this resistance 2 ohm I show here. Then there is a voltage source, but for calculation of RTH, we have to short circuit the source. Now see, this is ideal source because they have not mentioned any internal resistance. So it will be a simple branch like this. Okay, we come to this point. So point A is here and point B is here. And then it will be the circuit, equivalent circuit. So remember, only this 2 ohm is the resistance. This battery is shorted. And then this is open here. Only point A and only point B. So directly we get the value of RTH. So this is the equivalent value of resistance, that is RTH. So here I will write VTH, what VTH value we were getting, and RTH value. Okay. And then RTH was 2 ohm. Okay. And now all the values we have calculated. Just to draw the Thevenin's equivalent circuit, this will be VTH, this will be RTH, then our points A and B, and then we reconnect the load resistance RL. This value VTH is 8, RTH is 2 ohm, and load resistance is 4 ohm. And what is the formula? Now suppose we assume that the current flowing through load resistance is I, then this I must be equal to VTH divided by RTH plus RL. And so let us introduce or substitute the values. VTH is 8 divided by RTH is 2 and RL is 4. So it will be 8 by 6. So it will be again 4 by 3 ampere. And since I had told you that current will be flowing from A to B, because these polarities were correct, since we got positive answer for VTH. So here in the bracket we will write from A to B. Okay. So again see, we are getting the same answer as we have obtained with the help of Kirchhoff's laws. Now let us solve the problem using Norton's theorem. So 5 ampere like this, 5 ampere coming out from this point, and then this source will go. So it will be like this here. Same thing for this other 2 ampere current source. Here I will show 2 ampere entering this node here, and 2 ampere coming from this node like this. Again we omit this particular thing or the current source, and we keep these points hanging. What is the first step in Norton's theorem? To remove the load resistor. So this 4 ohm resistor we will remove. Then the open terminals we will mark as A and B. So this step is exactly same as in Thevenin's theorem. So I will just mark these terminals A and B, and here I will write load resistance RL as 4 ohm. So first step is over. Second step is that whatever open points we get here after removal of load resistor, we have to temporarily short them like this. So we will short the points. What is the reason? The reason is that as per the Norton's theorem, whatever current will be flowing through this shorted branch or shorted link, that will be nothing but the equivalent current source IN. So we are interested in finding out the short circuit current in this particular link. So let us see the current distribution now. Okay, again, now see here, you get one loop here. Maybe we will need one current variable somewhere. We will start from this corner. 5 ampere current is coming over here. Suppose we assume that I current moves like this. Okay. Now 5 ampere is coming here. I is coming down. What would be current flowing here? It would be 5 minus I. Okay. So 5 minus I current will reach here. Now what happens at this node? 5 minus I coming like this, and this 2 ampere is added into that. So what will current will flow ahead? 7 minus I, because these two currents will add. So 5 minus I plus 2 is 7 minus I. This entire current 7 minus I will flow like this. So 7 minus I. So obviously in the short circuited link, as per our current distribution, the current would be 7 minus I. All this 7 minus I comes like this. Now see, this 7 minus I reaches here. What happens at this node? Out of that 2 ampere is going out. So what current will remain here? It will be 5 minus I. And now 5 minus I reaches here. At this node, this 5 minus I coming, and this I is adding. That means the current 5 ampere will be moving, and see here the current 5 ampere is moving outside the circuit. So this will be our current distribution. Now see clearly in which value we are more interested. We want to find out the current flowing in short circuited link, and what is the current flowing in that link is 7 minus I. Now see, only one closed loop is there. So I assume that this is the loop right from this point here, here, down, left, further left, and back to the original point. So let us write the loop equation. So see here, loop equation. So let us write loop equation very fast. Starting from this point, this to this, it will be minus 6. Then this point onwards here, no component. This to this, again no component. This to this, no component. Again this to this, no component. And from this point to the original point, it will be plus 2i. So minus 6 plus 2i must be equal to 0. That means 2i is equal to 6. That means I equal to 3 ampere. Here we can write that, hence current in short circuited path will be equal to, what was that current? 7 minus I. That means 7 minus, what is I? 3. Remember, even if you get plus or minus value, whatever value you get, you have to introduce here. If it is minus value here, you put here minus value. So 7 minus 3 is 4 ampere. That means a current of 4 ampere will flow through the short circuited link. And here itself the direction is very clear. Since the answer is coming as positive or plus, it means that this direction is correct. So finally we can write at the end that this current would be flowing from A to B. So we have calculated this current. But as per Norton's theorem, what is this value? This value is nothing but the Norton's equivalent current IN. Here I will write, hence Norton's equivalent current IN will be equal to 4 ampere. And we can say that it is from A to B. So this step is over. Now what is the next step in Norton's theorem? Next step is to find the equivalent resistance across these two open terminals. Obviously we have calculated this value while we were using Thevenin's theorem, because we don't want to waste the time in the same procedure. When we were solving the problem with Thevenin's theorem, we have already calculated RTH. And what value we have got for RTH? For this problem, we have got the value of RTH as 2 ohm. Since it is the same step to be implemented, we will not waste the time. So directly here I will write. Now here I will first write this IN that we have got. IN is 4 ampere. And what would be the value of Rn? Since Rn is same as RTH, then already we have calculated RTH. So this value is 2 ohm. So here I will draw the Norton's equivalent circuit. A current source IN, then a parallel resistance, its value is Rn, then our two ports, open ports A and B, like this, and then we will introduce the load resistor across the points A and B. So here it will be RL. So this is the Norton's equivalent circuit. Now what values we have got? For IN it is 4 ampere, that I write here. Rn it is 2 ohm, and what is RL? It is 4 ohm. And now suppose if we assume that the current in load resistor is some current I, then what formula we should use for I? The I must be always equal to the total current IN, then multiplied by a fraction, that is Rn in the numerator, and divided by the sum total of two resistances, that is Rn plus RL. Okay, so let us just put the values. IN is 4 in bracket, in the numerator Rn is 2, in the denominator sum of the two resistances Rn plus RL, that is 4. Rn is 2, so 2 plus 4. So further simplifying this, what we will get? 4 into 2 in the numerator, in the denominator 2 plus 4 is 6. So what answer again finally we get? Finally we get this answer again as 4 by 3 ampere. Since this current was coming to be 4 ampere and it was coming a positive answer, that means the current direction is from A to B. So here we mention from A to B. So here we can make a statement that same problem we have taken, we have solved it first with Kirchhoff's laws, then we have solved it with Thevenin's theorem, and finally we have solved it with Norton's theorem. But every time the magnitude of the current flowing through the given resistor as well as its direction comes out to be same with all these theorems and rules and laws. Okay, so this is in short the procedure of solving the problems having both types of sources, voltage sources as well as current sources. I hope that you will solve many such problems of this type and you will get a good mastery. Thank you.